So to set the ball rolling, shall we talk about what are the main barriers to a more widespread adoption of GANs in the industry? Who would like to start? Yeah.
I have a pretty big list. There are many issues. First one, we haven't reached the realism needed in many medium, like in image we're decent, but in video, text, and many other applications we're not doing great. And even if we're doing good, let's say in image, you have a model that's good, but then it's still you'll need a lot of filtering because it's gonna generate a lot of images which are not good. So we need to figure out some way to filter. Other things, unstable training, high computational demands, and legal issues which we're gonna talk later. And we need real-time. For many applications, they need real-time generator that works in real-time. And other thing, we need to ensure there's no sensitive information in the generated outputs. Because if you generate text and then there's address of people, or you have medical data and you have name of people, and you have to be very careful.
Hello. So Prashant was mentioning the book that I'm working on. So one of the chapters is on GAN, and when I started working on it, I realized it's not like that easy. The initial models, actually, I had to struggle a lot. Like I had 3 computers running for like 3-4 days. And when I look at the output, there's nothing actually. It's just, I just wasted a lot of time. So it took a lot of time to even fine tune and finally come to something like a simple application where I started by using those MNIST images of digits and trying to generate new ones. And I realized even for like small applications, you have to fine tune your generator and discriminators in certain way. And the way you feed your noise and the way you feed images and make them like compete against each other before you get something reasonable. But once you are able to fine tune, I was surprised that I was under the impression that the images that come out are going to take a lot of training. But if your model is like fine tuned after a lot of struggle, then it is surprisingly quick. It doesn't take that much time to really get decent results. I'm not saying we can get great results in short time, but then it becomes very easy. And what I understand, looking at like trying different applications is something that works in one type of problem. You cannot just use that same or slight deviation of that model for other type of problem. So I think getting started for a specific type of problem is going to be a struggle, and I feel that's one of the major barriers. But ultimately, we do get results, and then it becomes like a very surprisingly, like very pleasant surprise that we do get results. But initially, it is a struggle, and I think that's the first hurdle.
Hello. Okay. Yeah, I would like to mention 2 aspects. So the first thing is, what are we talking about when we talk about GAN? We're doing unsupervised learning, right? Basically, we're trying to just model. We're not trying to say classify objects like what deep learning have been very successful in the last 10 years. We're trying now to just have model of the world and condition on the arbitrary thing and then answer other things. So this is super hard. Unsupervised learning is one of the key research questions in all of machine learning right now. So, and GAN is a particular technology which has been fairly successful on certain things. And actually I have a journal, a long archive paper explaining the theory behind also why I think it's actually a very successful approach for multidimensional modeling. But you know, this is a hard problem. And then the other thing I would like to mention is just the stability of the training, which actually I touch upon in my talk. So if you miss my talk, one of the main thing I mention is that when you train neural networks by having multiplayer, like multiple objective to minimize, it's a very different game, to make a pun, than just minimizing of a single objective. And the techniques that people are using right now are not mature enough to actually, for deep learning, to actually have a technology which is just working out of the box. I would kind of like compare where we're at now with GAN to how deep learning was at the beginning of the 2000s, right? Where only a small number of group of people who were able to make them work, Jan LeCun included, but it was very, like, people had problems with local minima, didn't really know how to train them, and then suddenly it became, there's like techniques and deeper network, different architecture. It became like now much easier to make these things work, but GAN is not the case. Like our experience with the paper I mentioned, just empirically, that's why I said, like, you have to be a deep mind to do these experiments, because you need to have like a GPU cluster, I don't know, with 100 GPU. The reason you need that is because of the hyperparameter tuning, because as soon as you change something a bit, like you change the architecture, you change the objective, you change the algorithm, you change the task, suddenly things just break. And then finding out how to tune the hyperparameters such that it will work again, well, usually what people do is just do a big grid search, and each thing takes 1 day to train, so on a big GPU, so you need like a few hundred GPUs to do things efficiently. And so in our example, like, people now, what they do is they take a paper, and then you can actually reproduce the results by just using exactly what they've done. But if you change something a bit, then suddenly it doesn't work. So it's really hard to also make future progress in this field to just like say, okay, because you have a new interesting idea, but then suddenly you don't know how to tweak the hyperparameters to make it work.
So as several of them just mentioned, it's actually pretty hard to train a GAN because of things like hyperparameter tuning. But there's actually been a lot of work on reducing the importance of hyperparameter tuning for GANs. And I was just wondering, like, now GANs have been around for 5 years or so, right? And so in these last 5 years, what are the best practices that have emerged with regard to how to reduce the importance of hyperparameter tuning and make GAN training more stable?
Well, personally, I have not done a lot of hyperparameter tuning. I run my model on my computer. So, yeah, of course, there's a lot of trick though. But you can just use the standard hyperparameter. But that's for computer vision though. Keep in mind, if you change medium, then you need to change the architecture and everything. So some of the tools we generally want is we either want to use spectral normalization or some kind of way to enforce Lipschitz on the discriminator, or we use a gradient penalty. This is really one big way to fix instability, at least alleviate it. And then obviously there's relativistic GANs is another way I created, so.
Yeah, so, hello? Yeah, so like some of the best practices I have come across it obviously depends on the type of objective you have and kind of data you are using. For example, if we are trying to generate a new image versus new text, where text is contains sequences. And when we develop this architecture for generator network and discriminator network, so if we are dealing with image data, I think everybody knows that nowadays convolutional neural networks, they are the gold standard for working with image data. And the layers that we use, we select convolutional just because we are dealing with image data, and they work very well. But if you are dealing with text data which has sequences, some kind of either text or integers, so obviously LSTM is one of the best known type of layers that you can use. And also I have seen when we use activation functions in the layers, it makes a very big difference when it comes to GANs. So I have seen like some of the activation functions won't generate anything, but a specific one will give wonderful results. So it's not like the other deep learning methods where we can try different activation functions and there may be small difference between the results, some improvements. But here it can be like just black and white. You get something useful or you don't get something useful. So there are some like best practices like that, and probably Simon can talk about more on this.
Actually, I don't consider myself a GAN expert, so I'm a bit new to this domain. I'm trying to understand what's happening. But I've been roaming at Mila in the GAN reading group, and what I've heard over there, for example, is basically you just need to regularize. So gradient penalty, spectral normalization, changing the objective in some way, all these can be seen as some sort of regularization. And the kind of thing, for example, people used to say, like, oh, well, you need gradient penalty. Well, you don't need gradient penalty if you just do a different form of regularization. So it turns out that a lot of things people said, oh, you need to do this. It's actually not even the case. A lot of other ways can do the exact same thing. So people also, by the way, just they don't know what's happening. Like overall, like we don't know yet what's happening. We're basically figuring this out. Like it's an area of research which is very active. And so you get, and actually that's also what happening in deep learning in like 20 years ago, where you had all these like, you know, guidelines for practice, but which a lot of these has been superseded now with a bit more maturity. So apart regularization, the other thing which I think hopefully will become a big thing as is now is variance reduction. So, which is something I mentioned in my talk. And interestingly enough, variance reduction has been tried in standard neural network training for supervised learning, and it doesn't help at all. Okay, so it didn't make a big improvement there, and it has perhaps to do with the fact that, you know, we're not also just doing optimization. Generalization is what's important, and the way you train your architecture influence the learning biases that you have, and perhaps variance reduction is not helping in the case of standard supervised learning. But for games, the methods are just not stable at all. So I think here variance reduction will make a difference. And so ways to reduce variance is bigger mini batches or the variance reduction trick was as we proposed, but this was as, like this year. So it's very novel.
Okay. So to summarize, you guys brought up spectral normalization, gradient penalty, and relativistic GANs, and also changing the objective of the GAN, that is the loss function which we're trying to optimize. And you also mentioned variance reduction, which is the subject of your new paper, I believe, right? And you also mentioned that some of these things like gradient penalty, they're not really necessary if you use a different type of normalization. Is that right?
Of regularization.
Oh, sorry, regularization. Yeah, you're right. And yeah, so then moving on next, what are the obstacles to overcome on the engineering side to enable broader applications of GANs? For example, most of the GAN research right now focuses on generating images. And there's been some really good work from NVIDIA, I believe, on generating high-resolution images. But what about even higher resolution or videos? Like, what are the obstacles to overcome on the engineering side?
Okay, so for videos, I don't think we're ready yet, because right now we're able to generate images in like 720p resolution, something like that, but it takes days. And if you have a video with 10,000 frames, it's going to be way more difficult. But and the engineering side that we miss for video outside of computing power is two things: understanding motion and time. Because okay, for motion you need a discriminator that understands that as time move forward, things drop down. You know, there's gravity. So how do you enforce this prior in a model? It's hard. There's some research on it though, so, but not yet with GANs. And the other thing is time. Time is the most difficult one because right now you have a video. So what do? You take like 32 frames and you predict the next 32 frames, something like that, but you don't get a long-term consistency. So you need to encode like what happened before and use it to predict the future. But do you generate 1 frame, 32 frame, and how much can you retain from the video from an encoding? It's really tricky. And that's for the generator. And the discriminator part also, he has to see, okay, I give 1 frame to the discriminator. Oh, that's a nice image. All right, but it doesn't tell if the video makes sense as a whole. And we cannot make a discriminator that takes a whole video. It's crazy. We have to kind of encode the video. And how do you encode it? How do you... So yet there is a big engineering step to be done. And the next thing, we need better label data for video. Like we need, ideally we would need to have a script. You know, imagine we have a TV show, we have the script, the whole script of the TV show, and we have the video. That really helps because then you can generate, you know what to generate next. Okay, I did this part, I need to generate the other part.
I think one key word here is conditional GAN. Like just unconditional GAN, I think, is not a really meaningful task. Like, okay, you generate pretty pictures, but like there's so many different things you could generate. So, so Alexia already kind of like hinted when you say, oh, I want to generate a video, but I have a script. So I can condition on the script saying what I actually want to generate. And so I think once you start to actually have a bit more side information of what you're trying to model, I think you'll actually have a higher chance of successful. Because also I think the problem of just generating videos is ill-defined. So which is also why actually in general there's a no free lunch. Like you're trying to generate high-dimensional data. There's no way you can just model arbitrary high-dimensional data with a few number of samples.
The videos yet because I'm still struggling with the images. That itself is, I think, a very complex task, and especially like if you are trying to do even images, multiple types of images at the same time, so that itself increases a lot of like difficulty. So I think we are not there yet for video. I have not seen any really useful model yet.
Perhaps also I'd like to mention the interesting problem of text, because here there's a technical problem that because we're using...
There's going to be a question.
A question on text? Well,
text.
Anyway, I'll still mention it now. So the issue is that you have... so you're doing these continuous models where you can easily backpropagate through them. So when you have continuous data, it's all nice. Once you start to model data, which is more like discrete, like units of text or anything which is combinatorial, then it becomes tricky to just know how to do these gradient methods. And that's why text also is not really good yet.
So I have a question about conditional GANs, or we could move on to text. What do you guys prefer? Okay, because Simon just brought up conditional GANs, and one of the early conditional GANs, which perhaps a lot of you are familiar with, is called pix-to-pix. That was for image-to-image translation. Now, in pix-to-pix, they use both a discriminator to provide a GAN loss as well as a standard L1 loss, which could just as easily be an L2 loss or something. And that got me thinking. You see, nowadays we don't talk about convolutional neural networks that much. Instead, we just have convolutional layers in some larger network architecture. And are we getting to a point where we don't really care that much about GANs as a standalone neural network, but instead just adding discriminators in other architectures to act as an additional loss function?
Okay, can you explain what you mean? More multiple discriminators or multi?
What I mean is like we can have a regular L1 or L2 loss, and then having the discriminator just provides an additional type of loss. For example, if you remove the discriminator from pix to pix, it will still do something. It will still maybe not give as nice images, but it will still be useful. In a similar way, one could perhaps bring in discriminators into existing neural network architectures for things like generating videos or text and stuff like that.
Yeah, I've seen a lot of work that in the end they penalize for X, Y, Z, so much things, because in the end, yeah, it's engineering. You penalize for everything you want. You want pixel quality, you want this and this. So I think we're gonna see a lot more of that, because as things get better, you don't just want to generate, you want, like, you have specific thing, you want quality and this and that, then you can just penalize and get them.
Actually, so I have a paper which is exactly saying a bit along the lines of what you're asking, which is the, and this paper was basically me and my students trying to understand GAN and then realizing why actually it could make a lot of sense to do high dimensional data modeling. And the idea is when you do standard statistical modeling of density estimation, you just minimize the log likelihood, you maximize the log likelihood, which is basically the same thing as minimizing the KL divergence between the true thing you're trying to model and your proposed distribution. And the KL divergence for high dimensional object like images does not make any sense, because the KL divergence, all it cares about is, do you put the mass exactly at the right place? If you put the mass slightly close, but not at the right place, it doesn't matter. It's the same thing as if I put the mass super far, far being like, say, visual similarity or L2 distance or something like that. And so KL divergence is actually a really bad idea for high dimensional modeling. And you can think of the GAN objective, the discriminator, is in some sense implicitly defining a divergence which is more suited for the task you're trying to solve. What do we mean by suited? Well, okay, if what you care about is to generate pretty pictures, well, you want distribution which generate pretty pictures, i.e. if the mass is on something which looks visually similar to the true distribution, you're happy. You don't care that it's exactly the right place, which the KL would like to do. And so that's actually why then the question is, okay, well, what kind of discriminator should we use to encourage specific different properties? And actually that's the thing we're trying to highlight in this paper, just saying as a, like, oh, we should look at these things. Like and it's, I think the name of the paper is something like adversarial divergences or good task loss for general modeling or something like that. You can find it, it's on arXiv.
Thank you. So why don't we talk a little more about using GANs to generate text, and what are the challenges involved in that?
Okay, so I'm not an expert, so I won't say much on this, but yeah, it's mostly just that we were dealing with discrete data, so we cannot take advantage of backpropagating through a discriminator and giving this signal to the generator. It makes things way more complicated, and it's not clear that GAN are necessarily the best way to deal with that, at least for now.
So text data is a unique type of data compared to like image data, where you have like the words in a specific sequence, and that makes sense. And the problems, like for a second, if you forget about GANs, even trying to develop some kind of classification models with deep learning, there are issues when we use recurrent neural networks, where we have like two words in a sentence or maybe some articles which are related to each other, but they are separated by big distance. And that's where like LSTM comes into picture. But generating new text, that's, I think, a very challenging problem. I have not myself started working on that because I'm still struggling with the image, but I can see why it is such a difficult problem. I think there was a news where somebody wrote a script on totally AI-based. So that book was written basically by using, I guess, GANs. And also, like, it could have applications in generating new music, but for the time being, I don't know whether we have technology to reach that there.
Yes, actually, I want to again step out a bit back, right? So the idea here is GAN and text. So there's not a good fit yet because of just technical reasons. But generating text is pretty good at this point. I don't think generating images is better than generating text. There are technologies which exist, and OpenAI was afraid of releasing some of their language models because they were afraid we would do fake news and this kind of stuff. So, so right now there's perhaps a misfit between the GAN approach and generate discrete data, but just if we want to do unsupervised model of text, there's other alternative approaches right now which has been a bit more successful.
It's still not that great. They exaggerated. Let's just be clear about that.
Well, my point is, it's not worse or better than the images. I don't think that we say the images are good or better than the text.
For us, it looks better because we're visual, but like in statistical sense, I agree. But as a human, I say, oh, I like it's nice. The image looks, but I see text and I see that's like nonsense. Like. I'm just saying, hey, you can read it, but there's not much coherence.
I don't know. Have you looked, like recently there was one where they had an essay prompt and it was graded by humans and it was about climate change. I read it and it was pretty impressive actually. Okay. So for me, I was as impressed by that than the pretty picture I showed over there of the guy.
I'll need to see that.
You heard it here first. Don't use GANs for text. There's other stuff to use for text.
Well, for now. I mean,
now, yeah.
I think you try. I mean, and hopefully it will work at some point.
Yeah. So what do you guys think is the untapped potential for GANs, and if we overcome the various obstacles that we mentioned here? And also, what are the legal considerations involved with GANs?
Okay. So I think for the potential, if we look in the far away future, then maybe one day it's gonna democratize art. Like people could do their own art. Someone wants to do their own TV show, they can generate one, build one. Like build their own movie franchise or comic book or whatever. And that's the far future. But in the short term, it's just going to be an help for, I see that as an help for artists and for medical, or just as an add-on. We think that AI is going to like take over everything and remove the jobs, but it's not the case. It's just going to be an add-on. For example, you're an artist, you do a model and you want to animate it. Then you have a GAN that animates it and you just fix the small error. Or you create models of a 3D model of something, you just generate for some of them, you take them as inspiration and you tweak them a bit and then boom. It's just to make your life easier.
So like I also feel the technology is very promising. There are so many possibilities. Just like sometimes I think like the way we do our work in a day or get busy with few things, have some discussions with people, and sometimes those ideas carry on into our dreams. So and those dreams are like newly generated kind of dreams. And I think GANs have that potential that it can take the input and create those kind of realistic kind of things that may start making sense when the system like perfects over time. But I think I feel it has a lot of potential, and especially for those people who are working in research field, this is a very fertile field, very active, and a lot of people are interested in this field. So a lot of possibilities are there, and a lot of things can be done. and also needs to be done to go to the next level. So I feel excited about like this field, and I see great things happening in future.
So GAN is for generative modeling. So what's the use of generative models? It's very wide, right? So I think helping artists is kind of cute, but for me, like the kind of problems I find where it's a bit more useful, from a more useful aspect, would be, for example, denoising, which has already been used, like completing simulation. So for example, in robotics, it's really expensive to run robots in the real world. We have simulator instead, but the problem is it's really hard to have a very realistic simulator. Well, you can augment these simulators with perhaps a bit of generative modeling coming from a GAN or such. Perhaps then you can get much more realistic simulators. And the idea is, at the end of the day, you want to have a model which helps you understand the world so that you can use it, to answer questions, to fix problems, fit in missing data, all these kind of things.
I think this is true, but in the end, when people are going to know about GAN, it's going to be because it's on their TV, on their everything. I think entertainment is going to be eventually, we're not there, okay? Let's be clear, we're far from it. But eventually it's going to affect entertainment industry, like generating your own content. I think, to me, that's...
Yeah, but one thing I want to kind of point out, which is happening with these kind of workshops, is that, like there's a lot of these research now is being done for, marketing in some sense. Like, you want your papers to be known. I want that, oh, GAN is known by my grandmother because I heard a song about GAN. And I think this is nice, but at the same time, you have to remember, are we trying to save lives? Are we trying to do science? Are we doing things such that people, tell us, oh, we like what you're doing, which is what entertainment is doing, or you actually have a bit more content and something where you actually have control over, which is your own, not the perception of people, but actually the content of what you're doing. So I think deep learning, in particular, like the domain, is now quite, fertile on Twitter. They're kind of going into these Twitter feed and thinking about how many Twitter followers they have. And I'm pushing back against this. And also I'm trying to help the students at Mila to kind of get a bit more distance about that, because they get in these cycles where they want to get more followers, and then let's have this cool application so that everybody knows about it. It's like, okay, well, I mean, you can also go to Hollywood if you want to do like TV stuff. Just a different perspective.
But I'm just not sure what's the link between Twitter and everything. I'm just saying art. It's going to help push art and help people create their own entertainment and just democratizing art. That's all I'm saying.
I agree with that.
Okay.
Oh, okay. So do we have time for some questions from the audience?
We have 1 minute. So, okay.
Okay, this guy has a question.
Thanks, that was a great panel. So one thing I just wanted to really quickly ask Simone, you mentioned during the panel and also during your talk as well, which was great, you were discussing KL divergence and how it's problematic in the context of GANs and that kind of thing. Recently, there's papers published on using different cost metrics, different distance metrics, such as like Wasserstein distance as a metric for for those confined dimensionalities that you were talking about. Could you speak more to that and what the research directions are in that kind of a space for the context of GANs?
Yeah, thanks. So, and actually, Wasserstein has nicer properties than KL, in particular because it includes this distance notion on the input space. But in the paper that I mentioned, adversarial divergences or good taskless for generative modeling, we also address the fact that actually Wasserstein, the normal Wasserstein distance has very poor sample complexity. And so when people use Wasserstein GAN, they actually don't use the standard Wasserstein divergence. They use what we call or other people have called a parametric version of it. And the fact that it's parametric gives it better statistical properties, which is also why it works. And that's another thing we highlight in this paper is that going from non-parametric, very powerful divergence like Wasserstein to something which is parameterized by a neural network actually makes a huge difference, both theoretically and perhaps in practice, though this is also like all stuff we're figuring out.
We can have one more question if you like. No questions? You got to follow up, okay.
You mentioned in the paper that you were talking about a little bit earlier that you currently haven't implemented ADAM or fancy momentum stuff in your gradient calculation and that kind of thing. We find that in transfer learning or in short, like one-cycle learning, that using discriminative learning rates is really, really valuable, and using them in conjunction with changing the momentum as you do multiple epochs is extremely beneficial to quickly learning on transfer tasks and that kind of a thing. And presumably that's going to be useful, or it's a useful notion, at least I think. How does that present itself? Could you speak more? The question really is, could you speak more to what specific challenges you're having in finding momentum for that method, and what research directions there are in that kind of thing?
Sure. So basically, momentum is fine. We can add momentum and it works fine. The thing which doesn't work right now, we have not experimented that much, and also we didn't have a big DeepMind cluster, was that using diagonal scaling of the step size by dimension, like is happening in ADAGRAD or ADAM, we were not able to combine it nicely with the variance reduction. In particular, ADAM is normalizing things by variance, and if you reduce the variance, suddenly you had way too big step size and it was diverging. So for example, we just need to find a version now which works nicely with variance reduction. And also there's another issue that people use spectral normalization, batch normalization, this kind of thing in this network, and these are all bias method, like bias in the sense that when you take an expectation over your mini batch sample, you don't get the true gradient. And variance reduction techniques and all these kind of things were usually more developed for unbiased estimate, and so how to combine it with bias estimate is also an open area of research.
I think we don't have time.
All right. Thank you very much, guys, for coming here. Thank you, Simon, Dr. Intra Rai, and Alexia for coming.
Thank you.
It was a great panel discussion.